Alright, welcome back. We are continuing to talk about our repeated measures ANOVAs. Again, our repeated measures ANOVAs are run when we have a single factor, and a factor, again, is either an independent variable or a quasi-independent variable. It's just different groups of people. The only difference is if you create them by manipulating an IV or by just measuring a pre-existing quasi-IV. So, at the end of the last video, we talked a little bit about the biggest difference between repeated measures and between participants ANOVA, which is that our F ratio changes a little bit. The factor of individual differences disappears from the numerator of our F ratio. The reason why? Because our different samples of scores are all coming from the same people. We know that there's no pre-existing individual difference between those groups. We know that our first condition doesn't differ on that DV on average compared to the second or the third or however many we have. The reason why we know that for absolute sure is because it's the same people. And what we talked about was that we are going to be eliminating individual differences from the within groups variance as well to turn it into what's called the error variance. So individual differences disappear from the numerator automatically just by the nature of within participants design. But now we have to factor for people in the same conditions differing from each other. Just the fact that individuals are going to differ on these DVs. So we're going to have to figure out a way to mathematically pull those individual differences out of the denominator. Here's how we do it. We calculate what is called between subject variance. So, oh boy, another kind of variance, huh? We subtract that variance and then we just remove it from the denominator before we calculate our F ratio. So, important note, statisticians are not real creative with the names they give to things. Between subject variance sounds a lot like between groups variance. Between groups variance is our numerator. Between subject variance is a portion of the denominator. And again, it refers to how much subjects differ or participants differ from each other instead of how much groups of participants, groups of data differ from each other in terms of those individual differences. But long story short, it's not that complicated to calculate. First, we calculate sums of squares and degrees of freedom the same exact way we did in the one-way ANOVA. Look at all these guys. Oh, it's our new friends from the last module. So many formulas to look at. Okay, let's get those out of the way. It's probably a little bit overwhelming, but again, you can calculate all that stuff just the same way you did in the one-way ANOVA. What changes is, after you calculate all those things, you calculate a new score. And that score is each person's total score across all conditions. Remember, you're measuring each person multiple times, at least 3 times. So all you're doing here is just adding up their scores. The book calls this total P, or participant total. Others sometimes call it the row total or something like that. We're just going to call it P here. So let's say you are measuring someone's depression levels over time and their scores are 26, 24, and 18, the same participant. Their P, or their total, would be 68. You just add them all up. So calculating P just means take each participant, add up all of their scores on the DV together, and that is the P for each one. So you wind up with one score for each participant. That's just all of their measurements added up. Very, very basic to calculate. Then we take that P factor and we calculate what's called, again, a between subjects sum of squares. That's how much, again, individuals are typically differing from each other. It's a similar formula to that between groups sum of squares. Notice it looks almost exactly the same as that formula, except there's a little bit of a difference over here. It says between subjects instead of just between. But also, instead of x's, we see p's. We're going to be plugging in individual p totals for each participant, and then we're going to be taking a sigma p total across the entire data set. So notice that sigma p total is exactly the same as sigma x total. It's just every single score in the data set all added up. So it's not too tricky to calculate. And good news, you never actually have to calculate it. You just have to understand how this works conceptually. Notice we're not working with real data in this module. So you should understand this process conceptually, but you are not actually going to be plugging numbers into this formula. So we then take that between subjects sum of squares. We subtract it from the within groups sum of squares, and then we just go get the mean squares and the F ratio the same way they were before. So all that we're doing here is we're calculating this different source of variance from individual differences in within the same groups, and then we're just pulling it out of that within group sum of squares before we create the mean square within and the mean square between. So you're just adding one extra step that's, again, eliminating individual differences from our within groups sum of squares. And again, ultimately our within groups variance. So that's the difference in calculation. Again, be familiar with it conceptually. Don't worry about actually using those formulas or plugging scores in. Here's a little bit of a conceptual idea here. Again, if you're giving this some thought and you're looking at the characteristics of repeated measures and between participants designs, you might be thinking, gosh, it seems like the within participants design makes a lot more sense to run. It has a lot of advantages. Like we just said, it makes the F ratio a much more accurate estimate of variance. That's what we want. We want accuracy. And we're going to get a cleaner measurement of whatever effect our treatment might be having. So that's really good from a research perspective. It also increases the power of the design. Because it eliminates that one source of variance, it's more likely that if there really is a meaningful difference between the populations, that your study will detect it, because one sort of source of noise in those individual differences has disappeared. It's also more efficient. You don't have to measure as many people because you're getting multiple measurements from the same folks. You get more data while measuring fewer people. So it can be more resource effective as well. So why not just run this every single time? In fact, not only are repeated measures ANOVAs not that common, they are a lot less common than our one-way ANOVAs, even though we have these big advantages here. So why? Well, the biggest downside is that within participants' designs have run risk of what are called order effects. Order effects basically come from the fact that you're measuring the same DV several times. So because of that, you naturally have to measure it once, and then a second time, and then a third time, etc., etc. You're measuring it in a specific order. Here's the thing. As people get measured on the same variable multiple times, they can start to experience what are called order effects. Order effects are things that change their scores just based on the fact that they've done that same DV measurement multiple times in a sequence. So order effects are anything that result from being tested repeatedly on the same DVs. Here's some of the really common ones. If you keep giving people the same task over and over and over again in different conditions, they're going to get tired or bored. And so their attention is going to slip, their performance and reaction time may drop. Or if it's something skill-based or memory-based, they're probably going to get better as you keep measuring them because of practice. If you're giving them the same questionnaires, they're probably going to remember their past responses and alter their responses because of that. And as you keep giving them more measurements in different IV conditions, they're probably going to guess the hypotheses, or at least have a better shot at guessing those hypotheses. All of these are things unrelated to the IV that can influence people's DV scores. And that's really, really bad. Anything that influences people's DV scores that's not the IV is to be avoided. So order effects like these tend to drop when you put more time between your measurements. So what's called longitudinal studies, where we track people for weeks or months or years or decades, those order effects aren't as big of a deal. But generally, especially if you're measuring people over a short period of time, order effects become bigger and bigger problems as you're measuring more and more people. So a 2-sample within participants design is probably not going to have as big of an issue with order effects as, say, a 4-sample repeated measures ANOVA type of situation. So we don't use this type of design much. When we do use it, again, is those longitudinal studies where we track people over time. So next up, that is the end of our repeated measures ANOVA. Next up, we are going to talk about situations where we have multiple factors, or this next video is also known as "This wasn't complicated enough already," because I know you've all been thinking that. You're probably getting bored with how straightforward and simple you're finding all of this. So we're going to kick it up a notch. We're going to talk about a slightly more complicated design, but don't fear. As always, there's only a few basics to get a handle on for this type of design. I will see you there.